Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the last video on a series of videos about derivatives of functions and an introduction to derivatives as a function. So we have not actually officially stated any of the derivatives yet. So I haven't said like, oh, the derivative of the sine is, or something like that. This is still working on the theory of derivatives. So in this final video in that series, we're going to talk about higher order derivatives. Second, third, fourth, fifth derivatives. And we're going to start with a conceptual question. If you were in a car, blindfolded, ears plugged, and all five senses neutralized, what quantities would you still be able to perceive? You should pause the video and think about that. Spend a little bit of time thinking, what would you feel if you were in a car and could not sense anything other than motion? Now, reality is, if you've come back from pausing, you cannot feel the velocity. You can't feel how fast you're going. And I'll give you an example why. We're on a planet going very fast. You don't feel that. So when you're in a car going 65 miles an hour or whatever, you don't feel that. What you feel is acceleration. You feel it when somebody's speeding up or slowing down. That force is what you feel. Just like we feel acceleration due to gravity, that's called weight. We feel that, but we do not feel the velocity of being hurtled through the cosmos, because that's just a velocity, not an actual acceleration. Another thing that we feel is what we call the jerk. So two things we feel: acceleration and jerk. The jerk is to acceleration what acceleration is to velocity. So it's a change in acceleration. So acceleration is a change in velocity, change in speed, if you will. And jerk is called the change in acceleration. And that is actually used in mathematics and physics, so we will be using that word quite a bit. Physically, the jerk you can think of as that uncomfortable sensation when a car suddenly stops, right? That quick difference in acceleration is called the jerk. Now, before we can go into computing a higher order derivatives, we have to actually talk about them. So the second derivative of y equals f of x is written as f double prime of x, which is also written in Leibniz notation as d dx of d dy, or d dy dx. So d dx of dy dx, which is the derivative with respect to x of the derivative of y with respect to x. Or another way to write that is the second derivative of y with respect to x twice. The third derivative is f triple prime, the easier way of remembering it, or the third derivative of y with respect to x 3 times. And then you can go for any other higher order derivative, but when you go to higher order derivatives, there's just a simple little change. For the Lagrange notation, first derivative, second derivative, third derivative. But once you get to anything beyond the third, you start using superscripts. And you put them in parentheses so they're not mistaken as powers. So the fifth derivative in Lagrange notation is f with the superscript of a parenthesis 5 and parenthesis. That's just a heads up. So anyhow, those are the higher order notations. Let's go ahead and use those higher order notations right now. So here's a function. Find the fifth derivative of this function, which means you can't just skip to the fifth. You have to go through all other derivatives. So f prime of x, it's going to be a lot of handwriting here. So I will pause and unpause so that I can quickly do that. There's the definition of the derivative. We're going to plug in this x plus h into our function. And I tried to color code it here. So the red was me plugging in x plus h. The green is just the original function that you subtracted. Now you're going to multiply that out. And multiplying this out requires either patience, because you're multiplying binomials against themselves multiple times, or better yet, Pascal's triangle. So I'm going to quickly multiply these binomials out using Pascal's triangle. And again, I tried to color code. I actually changed some colors there. So the red ink is to do with the expansion of x plus h to the fourth. The black ink is to do with the expansion of x plus h squared. The blue ink is just the x plus h, and the green ink is the same green ink from before. But now that we've done that, you can go through and cancel like factors. This x to the fourth will cancel with that x to the fourth. This negative x squared will cancel with that positive x squared. Let's see, what else do we have? This positive x cancels with that negative x. This positive one with that negative one. Looking through, I think it's just going to be combining like terms from this point forward. So let's go ahead and do that. You get down to this. I actually factored the h out as well, so that the h's cancel beautifully, and then we'll be able to do direct substitution. So via direct substitution, anything attached to an h will disappear, and you're left with a 4x cubed. Let's see, minus 2x, and then plus 1. So that is the first derivative of that function. Now we're going to move on to the second derivative. So first derivative done. Let me clean up that plus. It's a little bit ugly. So first derivative done, then you move to the second derivative. And you think, oh my gosh, we've got all this work to do all over again. Well, it gets a little bit easier as we move forward. One thing I want to note here is, since it's the second derivative of x, that instead of f of x plus h minus f of x over h, it's f prime of x plus h minus f prime of x all over h. So whatever derivative this is here, it'll be one less there. If it was the first derivative here, that is called the 0th derivative. The original function is called the 0th derivative. So it does actually make sense. Whatever derivative you're looking at, the interior of your limit will be one derivative less. So let's go ahead and plug this in. So again, in green is our function, our derivative, first derivative evaluated at x plus h. In blue is the first derivative just evaluated at x. We're now going to go ahead and expand those. Again, I'll just quickly use Pascal's triangle here to do that. That's the limit as h goes to 0 and a big old fraction bar. You get down to there, and then one last time we just cancel off 4x cubed with that 4x cubed, this negative 2x with that positive 2x, the positive 1 with that negative 1. And then with the remaining terms, I will factor out an h and see what we get. Here we are. I'll go ahead and cancel those h's, and we can do direct substitution. So I'll just scroll down a little bit and say just direct substitution. Let all the values of h go to 0, and you'll have a 12x squared minus 2. That is the second derivative of f. Now we move on to the third. Notice that actually wasn't as bad as the first derivative. They get easier as you move on, for at least polynomials, I should say. It's not true for many other functions, but for polynomials, the derivatives get much easier as you move forward. And just like I wrote last time, you'll want to go ahead and note that the third derivative is the same thing as the limit as h goes to 0 of the second derivative evaluated at x plus h minus the second derivative evaluated at x, all being divided by h. In this case, we have the limit as h approaches 0. This time it's short enough for me to actually write as I do this. So we have, let's see, 12 times the quantity x plus h and quantity squared minus 2. And then we're going to subtract the second derivative evaluated at x. So that'd be 12x squared plus 2, because you're subtracting that entire statement. It's all over h. And now we will go ahead and distribute things out. Limit as h goes to 0 of, this will be a 12x squared plus 24 hx plus 12 h squared minus 2 minus 12x squared, and then a plus 2. That was just quick multiplication out. Hopefully everything was right. Cancel anything that's alike. So 12x squared cancels negative 12x squared, negative 2 and positive 2 cancel. Factor out the h and cancel. This time I'm just going to say this h goes into those like this. There we go. And via direct substitution, we get 24x. And anything else? Nope, h goes 0. So 24x. And that's the third derivative. Now we move to the fourth. Notice I'm using the superscript parenthesis 4. The fourth derivative is just a limit as h goes to 0 of the third derivative evaluated at x plus h minus the third derivative evaluated at x all over h. You can see this is getting faster. This is the limit as h goes to 0. Take that third derivative we just found, plug in x plus h, subtract off the third derivative evaluated at x, and divide all that by h. You'll see that 24x cancels with 24x, and the h's will cancel, and this will be 24. I'll let you kind of investigate that, but it is true. And now, the fifth derivative. Again, limit as h goes to 0 of the fourth derivative evaluated at x plus h minus the fourth derivative evaluated at x all over h. Well, that's the limit as h goes to 0 of 24 minus 24 all over h. 24 minus 24 is identically 0, not approaching 0, but identically 0. And anything that's identically 0 over any non-zero number, that is 0. Remember, h is approaching 0, it's not identically 0, but the numerator, totally 0. So let's look back at our journey here. The first derivative, well, the 0th derivative, the original function, 4th degree polynomial. And then we took a derivative and it became a 3rd degree polynomial. And then we took another derivative and it became a 2nd degree polynomial. Then we took another derivative and it became a 1st degree polynomial. Then we take yet another derivative and it became a constant, a 0th degree polynomial. And we took yet another derivative and it turned into 0. A 4th degree polynomial, 5 derivatives, we ended up with 0. This is a pattern I want you to recognize. That if I had a high degree polynomial and I took a bunch of derivatives, it would be 0 after you took all those derivatives. Well, we'll find out in a moment. Another thing I want to draw your attention to, I didn't actually have to compute anything once I got to the 4th derivative. Once I found that 4th derivative was 24, the 5th derivative is just asking, hey, what's the slope of that 4th derivative? Well, that 4th derivative is y equals 24. So that's a horizontal line. It has a slope of 0. So I don't actually have to compute anything there. I know that derivative would be 0 because the slope of the line y equals 24 is 0. That's the slope of this line. So that's a kind of a cool way to do that problem. Also a lot of practice, right, on Pascal's triangle and multiplying, all that fun stuff. Don't worry, it gets faster. So let's summarize. Based on the last example, which was a 4th degree polynomial, and yet we took the 5th derivative, what could you say about the m plus 1st derivative of an mth degree polynomial? Well, based on what we just seen, the m plus 1st derivative, m plus 1 of x, would be 0 if f is an mth degree polynomial. If you took m derivatives of it, you would end up with a constant, and then the derivative of that constant would be 0. So that's based on our last example. It's not a proof, but it's based on the last example. And in our final example here, I do need to mention a few things. So it is often the case in physics that we use S for position. S of t equals position. Spatial position, really. And the derivative of that we would call the velocity. It's not just speed, it's speed with a direction. And the second derivative of that, which is the first derivative of the velocity, is called the acceleration. And if you really want to get fancy, the third derivative of position, which is the second derivative of the velocity, which is the first derivative of acceleration, is called the jerk. Now, think about this. You have some time element here in your position. You start from your house in the morning, you drive for a while, you get a certain distance away, you're at work all day, and then eventually you go back home. Okay? The units for position, let's say, are miles. And T is in terms of hours. How many hours do you spend sitting at your desk or whatever it is, right? A derivative is a slope. Slope of a tangent line specifically. So it's rise over run. So that should make sense. If I take miles and divide it by hours, rise over run, that's a velocity. Miles per hour. If you were then to look at the velocity curve, the velocity again is in miles per hour. Time is still in hours. The derivative of the velocity would take, again, rise over run. It would be miles per hour, or in other words, miles per hour squared. And while that's not how we measure acceleration on our planet, we do measure it in meters per second squared, and that's a distance per time squared. So that's a good justification why the derivative of the velocity ends up being an acceleration. The acceleration is how quickly the velocity is changing. It's another way of thinking about that. Now that entire conversation is necessary so we can start this question. That figure down below shows the graphs of three functions, obviously, A, B, and C. A being the blue, B being the green, C being the red. One is position, right? So S. One is the velocity and one is acceleration. And they're asking us to identify each curve and explain the choices. So given a curve like this, here's how I go about it. I look at all of these curves and I identify where their slopes are zero. Right here. So I look at that and I say, okay, is there any other curve? Because remember when we graphed, when we graphed the velocities and stuff like that, or sorry, the derivatives, every time that we had our function with a horizontal tangent line, we knew that the derivative would cross the x-axis. But notice, where this has a horizontal tangent line, there's nothing that's crossing the x-axis. So A does not have a derivative in this picture. If A did have a derivative in this picture, then its derivative would cross the x-axis here and, by the way, here. So A does not have a derivative in this picture. So therefore, A is not the position function, because the derivative of the position function is a velocity, and they told us one of these pictures is the velocity. And A is not the velocity, because they said one of these pictures is the acceleration, and the acceleration is the derivative of the velocity. So because this blue curve does not have any apparent derivative curve sketched here, this blue curve is the acceleration. It must be, because that's the only curve that doesn't have a derivative sketched. Remember, they gave us position, they gave us velocity, and they gave us acceleration, which is S, S prime, and S double prime. The only one that doesn't have a derivative graphed is S double prime. It doesn't have its derivative, S triple prime, graphed. So A must represent the acceleration. I'm going to write that in there. That's one out of the way. Great. So now I can erase these. I'll move on to B. Now B, if I look at this, B has a flat line, flat tangent line right there, and it looks sort of, if it lined up perfectly, it looks like the blue curve crosses the x-axis or the t-axis identically when B has a horizontal tangent line. But just to verify that, let's go ahead and take a look at values of B prior to that. The slope of the tangent line here is positive, and notice A is above the x-axis there. The slope of the tangent line here is positive, but not as positive, and guess what? A is positive, but not as positive there. The slope of the tangent line here is positive, but not as steep as it is here, so slightly less than the value, the steepness at this point. So they're a slightly smaller y value. Let's see. The slope of the tangent line right here is negative. And notice the blue curve is negative at that point. Slope of the tangent line here is negative, and notice the blue curve is negative at that point. Slope of the tangent line here is negative, but not so negative. It's getting slightly less negative. Well, the blue curve is getting slightly less negative. Slope of the tangent line right here, it's still negative, but almost zero, and so is the y value there. So it looks to me that the blue curve A is the derivative of the green curve B. So B must be the velocity, because if A is the derivative and A is the acceleration, well, acceleration is the derivative of the velocity. All right, all that being said, let's just verify, and this might be actually challenging, let's verify that C must be the position function. Well, this is actually not super easy to do, only because our position function doesn't ever reach a horizontal tangent line. But we could say, notice this red curve has a, well, I should use the color different than red, has a positive, 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 positive tangent lines always. Always the tangent lines are positive. Although they're approaching a height of zero, or a slope of zero, they're still always positive. And notice B is always positive, 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 positive. Although it is approaching a height of zero, it is still always positive. Thus, B does look like it's the derivative of C. And since B is a velocity, C must be position. These are really cool problems. I highly recommend, if you didn't get that, to spend some time reviewing that. It is a very, very big, important topic in differentiation, that you really understand the link between the graph of a function and the graphs of its derivatives, the first, the second derivatives. Very, very important.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.